Okay, yes. Many thanks, Lisa, for all these efforts to arrange the event. And good morning, everyone. My name is Xiaodong Luo. I'm from NORCE. So in this webinar, I'm going to present an ensemble-based workflow for subsurface characterization in underground hydrogen storage problems. And this work is done together with my colleagues at both NORCE and UES. So first of all, I'm going to briefly explain why we need to do underground hydrogen storage. So as many of you have already know, similar to natural gas, and hydrogen can also be used as an effective energy carrier. And in general, hydrogen storage would be useful for instance, buffering fluctuations of energy supplies and demands at different time scales, and also useful for ensuring energy security and strategic energy reserves. So in general, there are different forms of hydrogen storage, including surface hydrogen storage, underground hydrogen storage, and material-based hydrogen storage. To my knowledge, and at present, it seems underground hydrogen storage is the only viable way for long-term hydrogen storage at large scales to meet seasonal energy demands for our society. For the purpose of underground hydrogen storage, one essential procedure is to understand the subsurface first. So then this requires some workflow called subsurface characterization. So here by subsurface characterization, we mean the procedure that combines, say, certain numerical model and monitoring field data for improving our subsurface understanding at the field scale. So subsurface characterization can be used for instance, understanding hydrogen deliverability during the injection and withdrawal cycles, and studying the hydrogen checking mechanism, imaging potential hydrogen mitigation in the subsurface, and detecting potential hydrogen leakage in long-term operations. So in the petroleum engineering, subsurface characterization is also known as history matching, so which is the name that I'm going to use later. And then because of this connection, previous experience and working knowledge from oil and gas operations can be similarly extended to underground hydrogen storage problems, but of course the goals will be different. So here I'm going to present an ensemble-based workflow for subsurface characterization. So in an ensemble-based workflow, we typically start with an ensemble of, I say, initial subsurface models, and then we using a certain numerical simulator to run forward simulations to get an ensemble of corresponding simulated data. Now, of course, if we would always have a set of observed field data, then we compare the difference between the observed and the simulated field data, and then using a certain ensemble-based inversion algorithm to update the ensemble of subsurface models in such way that after model updates, the difference between the observed and the simulated field data can be reduced. So ensemble-based workflow is among the popular history matching procedures for hydrocarbon reservoir characterization in the oil and the gas industry. And its popularity is partially due to the foreign noticed practical benefits. For instance, the ensemble-based workflow is non-intrusive to the numerical simulators. So this means that we can use any numerical simulator as black box to just run the forward simulation and get a simulated data. And we don't need to know the details how this numerical simulator is coded. And the ensemble-based inversion algorithm is derivative-free. So this means that for the purpose of model update, we don't have to explicitly calculate the derivatives of the objective function with respect to the subsurface models. So this is a huge benefit in practical problems. And then from our experience, we know that the ensemble-based workflow typically can be applied to handle very big, let's say, subsurface characterization problems. And then it also provides a means of uncertainty quantification and risk analysis, because instead of, say, updating a single subsurface model, we are actually updating an ensemble of such models. So here I apply the ensemble-based workflow to a 3D underground hydrogen storage benchmark case. And then this subsurface model is taken from this previous paper. So in this subsurface model, the size of the model is 61 by 61 by 12. And in this model, there's only a single well bomb, which is used for both hydrogen injection and withdrawal. And then we run simulation of the subsurface model for 1,500 days. And we use Eclipse 300 as the numerical simulator. So here I show the, let's say, the spatial distribution of hydrogen in the reference model at different time steps. I'm not sure if you can see this video. Is that working well? Anyone can confirm that?
Yes, we can see.
Okay, that's good. So from this video, you can see that at the beginning, when no hydrogen is injected, so basically you will not be able to see any spatial distribution of the hydrogen. So after injection, and then you can see that there's a certain amount of actually hydrogen plume. Okay, I need to change. I think I need to change the, yeah. Let's see. Okay, I cannot stop the video. That's the problem. But anyway, so from here, I mean, after injection, you can see the spatial distribution of hydrogen around this single well bomb. But there's a unnoticed problem. That is, I mean, around this direction, we can see a strip of the subsurface area in which the hydrogen actually has mitigated into. So this means that the small part of hydrogen that actually stays relatively far away from the well bomb. So this is often referred to as the fingering formula in the literature. The fingering formula, I mean, at least in this case study, is not wanted, because from the perspective of hydrogen storage, if you want to take the hydrogen out during the withdrawal cycle, if hydrogen remains relatively far away from the well bomb, then it's going to actually affect the deliverability of hydrogen. And I mean, in this simulation, we know the actually the spatial distribution of hydrogen, because we assume the knowledge of the reference model. But in practice, normally what we would have is maybe some initial guess of what the subsurface would look like, and a collection of field data. So our question here is that can we estimate, or at least make some good estimations of the subsurface model based only on the information that we have? So to answer this question, here we conduct a his matching experiment. So in this experiment, the time period for his matching is also 1,500 days. And then we are going to estimate two types of petrophysical parameters. That is the X directional permeability and porosity on all active grid rocks. So in total, we are going to estimate around 89,000 parameters. And then we use number of production data from the single well bomb in his matching. But as we will show later, if we only use the production data from this single well bomb in his matching, then the his matching performance is not entirely satisfactory. So to improve his matching performance, we also additionally introduce some 4D seismic data set. And then we use an iterative ensemble smoother for model updates. So that's the basic setting in the experiment. And later we are going to compare the numerical results in 3 different scenarios. So they correspond, they are labeled as the initial scenario. So in that case, it corresponds to an ensemble of initial subsurface models. And there's no his matching conducted for model update. And the second scenario is referred to as the prod scenario. It corresponds to the situation that only production data are used in his matching. And the last scenario is referred to as the prod SAS scenario. So which corresponds to the situation that we use both production data and the 4D seismic data in his matching. And then we are going to compare the performance in these 3 different scenarios. So here first I present the performance comparison in terms of data mismatch and root mean square error in 3 different scenarios. So here data mismatch basically calculates the differences between the observed field data and the simulated field data, whereas root mean square error calculates the discrepancies between the reference subsurface model and our estimated subsurface models. So in terms of data mismatch, we can see that if we use both production data and seismic data in his matching, then we can get the lowest data mismatch in for both production data and the seismic data. But of course, in the second scenario, this prod scenario, we actually don't have any seismic data, so we cannot calculate the seismic data mismatch. And then we also obtain the same conclusion if we have a look at this root mean square error metric. So basically for both types of parameters, if we use both production data and seismic data in his matching, we can also get the lowest root mean square error. So which means that actually the model quality is the best after his matching. And here I show 3 types of production data that are used in his matching. The first one is the, let's say, the field production rates of water. And then the second type is the field production rates of hydrogen. And the last type is the well bottom hole pressure. And then in all these figures, you may notice some red dots. I hope you can see them because I think they are a bit small. So these red dots corresponds to the noisy observed field data, which are used in his matching. And these noisy data are generated by adding certain Gaussian white noise to the production data generated from the reference model, while the production data from the reference model is plotted in this yellow curve without any noise. And now all these blue curves corresponds to the simulated production data from the ensemble of reservoir models either before his matching or after his matching. So if we compare the profiles of these 3 types of production data, then we can see that again, if excuse me, if we use both production data and the 4D seismic in his matching, the actually the simulated production data can best match the observed field data in general. So this is in consistency with the results in the previous table. And here we also show another 3 types of production data. As a difference here, these 3 types of production data are not used as observations in history matching. So that's why in all these plots here, you will not be able to see any red dots. And these three types of production data corresponds to the total amount of hydrogen that are trapped in the subsurface and become immobile. So, and then the second type is the total amount of hydrogen that remain inside the subsurface, but still mobile. It means that they can still flow in the porous media. And the last type of production data is the total amount of hydrogen produced during the withdrawal cycle. And then again, we can actually obtain the same conclusion. That is, if we use both production data and the seismic data in his matching, then this simulated production data can match the production data from the reference model best, because in this case, we don't have any observed data in this case. Then based on the information from these predictions, we can actually evaluate the performance of underground hydrogen storage project. So the performance can be expected from three aspects. For instance, we can calculate how much hydrogen is actually trapped inside the subsurface due to these different tracking mechanisms, and then how much hydrogen remains inside the subsurface, but they are not trapped. And then how much hydrogen we can recover during the whole simulation time. In this case, other than these three scenarios, that is the initial prod and the prod size scenarios, we also add the numbers calculated from the reference model as the baselines. So the point here is that if the estimation is closer to the numbers, number in the reference model, then our estimation accuracy is the best. So if we compare these numbers in different aspects, as hydrogen trapped, hydrogen remain in place, and hydrogen recovered, and you can see that if we use both production data and the 4D seismic data in his matching, then the estimated number in these three different aspects remain very close actually to the numbers from the reference model. Actually, in terms of percentage, the maximum estimation error is no more than 3%. So that's actually something good for us. And then next, I'm going to show some of these estimated subsurface models. So here I show the reference porosity map on layer 2 of the reference model. And then this column corresponds to the results from the initial ensemble, and these two columns corresponds to the results from the final ensembles after model updates in both the prod and the prod size scenario. So if we compare the results in this column and the results in this column, so then we can see that if we only use production data in his matching, then basically we can see that the his matching algorithm cannot make substantial changes of the subsurface model. The main reason for this is because we only have a single well bore in the field, and then the production data from this single well bore has very limited spatial coverage, and then as a consequence, actually they contain very little information for model updates. So that's why after model updates, you can see that they look very similar to each other. In contrast, if we additionally include 4D seismic data into his matching, because 4D seismic data provide broader spatial coverage, then we can make more substantial model updates, and then and achieve better his matching performance because of these more substantial model updates. So that's the main message from these figures. And in the last, I'm going to show some of these, say, spatial hydrogen distribution in the subsurface. And again here, this corresponds to the map of hydrogen distribution on layer, I think it's on layer, yeah, on layer 1 of the subsurface model. And then the results in these 3 columns corresponds to the estimated hydrogen distribution maps in 3 different scenarios. And from these figures, we can see that in these 3 scenarios, no matter if we do model update or not, or no matter if we include 4D seismic data into history matching or not, these fingering phenomenon in this particular direction will not be able to be captured even after model updates. So I think this is a remaining challenge for our future work. So to conclude, in this talk, we applied the ensemble-based subsurface characterization workflow to a 3D underground hydrogen storage case study, and we showed that better data mismatch and the Loomis square error can be achieved after his matching, whether we only use production data in his matching or we use both production data and the 4D seismic data in his matching. But the problem is that if we only use production data in his matching, then we cannot make substantial changes to the subsurface models. And because of this lack of information due to the limited spatial coverage, in general, we kind of obtain inferior his matching performance in comparison to the choice that we use both production data and 4D seismic data in his matching. And then we also identify a remaining challenge that is actually in this particular case study as NIST, it's very difficult to capture the fingering problem in the reference model. So then I think we still have some challenge to tackle for our future research. So then this leads to the end of my talk, and now I'm happy to receive questions. Thank you.